5.3 Bisectors in Triangles. In this lesson, we are going to identify properties of perpendicular bisectors and angle bisectors. So this is an extension of our last lesson. Some vocabulary for us here. When three or more lines intersect at a single point, we say that they are concurrent. There's our co or con prefix. So they are together at this spot, at this time. They are together currently. They are together at this spot, concurrent. And the point at which they intersect is called the point of concurrency. Yay, math, for being straightforward. Well, let's look and see what this means to us. Our first theorem is appropriately called the concurrency, so that means the point where things come together, of the perpendicular bisectors theorem. So this theorem says we're talking about the point where the perpendicular bisectors intersect. So let's see what it says. The perpendicular bisectors of the sides of a triangle are concurrent, they come together, at a point, now we're talking about a point here, that is equidistant from the vertices. So let's go to our diagram and see if we can figure out what all these words mean. Now, just so you know, I am going to draw some lines and then erase them so you don't need to draw them. If we draw too many of them, the diagram will get all mixed up. So I'm just going to talk for a minute, so you just pay attention here while I talk for a minute. So our first part here says the perpendicular bisectors of the sides of a triangle. Well, what does perpendicular mean? Perpendicular means right angle, and bisector means two congruent segments. So we know what a perpendicular bisector looks like. So let's look at our bottom side here, side BC, and we are going to draw the perpendicular bisector. So we see here that it bisects and makes a right angle. So that's the perpendicular bisector of that side. And now we go to the next side. Let's do AC, the right-hand side over here. And we are going to draw the perpendicular bisector. Notice that we have bisected the side and it's perpendicular. That is the perpendicular bisector of that side. And let's do our third side here. We draw the perpendicular bisector. It bisects and it's perpendicular. So this is the requirement. The perpendicular bisectors of the sides of a triangle. So these are our perpendicular bisectors of the sides of our triangle. And then it says they are concurrent. That means where they intersect, three or more lines intersect, they are concurrent at a point. Right there, do you see where they all intersect there? So they intersect at a point, and here's where I'm going to erase, because we're not interested in the perpendicular bisectors anymore. That's simply a requirement. We need these perpendicular bisectors to find this point. So I am going to get rid of all my perpendicular bisectors here, because I'm interested in this point. But you can see where the perpendicular bisectors are, okay, are concurrent at this point. And what is special about this point? This point is equidistant from the vertices. So that means from this point, still using the eraser. So from this point, to my vertice, that segment, from this point to my vertice, from this point to the vertice, are equidistant. And look what it says here. The length of PA equals the length of PB equals the length of PC. These are equal lengths. So we can make them congruent, right, by definition of congruent. But our theorem talks about equidistant, equal lengths. Equidistant means equal length. So this theorem goes from the sides to the angles. So we're using the sides and going to the angles. And then we know that all three of these segments are the same length. Now, what's special about this point? Why do we care about this point? The point of concurrency of the perpendicular bisectors is called the circumcenter of the triangle. Now, let's figure out what that word means. The prefix circum, where do we use that? Circumnavigate. You circumnavigate the globe. What does that mean? That means you like sail around the entire earth. Or circumference, that's around the outside of a circle. Right? So circum means around the outside of a circle, and center, this is the center of the circle that goes around the outside of our triangle. So we have our point here, P, and we have 3 radii. And if we use these equidistant segments, if we use these segments that have the same length, and we set our compass, put the point in the middle and set our compass, we can draw a circle around the outside. This is an outside circle that touches all the points, all the vertices of our triangle. And think about it. This is a radius, this is a radius, this is a radius. They're all the same length. So we can draw a circle around the outside of our triangle that intersects each vertice. Having trouble with that today. The circumcenter is the center of the circle that contains each vertex. And we can say that we circumscribed a circle about the triangle. What does circumscribed mean? We drew a circle around it. Circumscribe, draw around. So that's fun. Now, the circumcenter can be inside our triangle. In acute triangles, it's going to be on the inside. I'm going to come over here. Obtuse triangles, got a word cut off there. It's on the outside. We saw this in our activity, which this is not a surprise. How would we draw a circle around this? It would have to be, now I'm going to draw this and erase it. It would have to be a really big circle, wouldn't it? To be able to touch all of the vertices. And back to the middle here, on a right triangle, guess where it's at? It's on the hypotenuse. Because think about what we have here. If we have a right triangle, we can draw a square or a rectangle, and our circle would go around it like that. So our triangle, a right triangle, would be in a half of the circle. Again, I'm going to erase all this, so don't worry about that. All right, let's look at our next one. The concurrency of the angle bisectors theorem. So what does this say? This says the point where our angle bisectors meet. Do you see that in the name? Concurrency, the intersection of three lines, three or more lines. What are our three or more lines? There are angle bisectors. So let's look at our theorem here. It says the angle bisectors of a triangle are concurrent at a point that is equidistant from the sides of the triangle. Think what the last one said. It said the perpendicular bisector of the sides was equidistant from the angles. So this one's going the other direction. So once again, let's look at our diagram. I'm going to draw lines and erase them. So just watch here. We are dealing with angle bisectors. So I'm going to draw my angle bisector. Going to draw my angle bisector and erase my little line here. And then I'm going to draw the angle bisector of this angle. And then I'm going to draw the angle bisector of this angle. Do you see how we have bisected those angles? You see that our bisect lines are congruent lines in our angles. Those are angle bisectors. But that's not what I care about. What do we care about here? We care about the point of concurrency. So we know we have these angle bisectors and they all meet at this point. And this point is what we're interested in. Because what about this point interests us? This point, the point of concurrency of our angle bisectors, is equidistant from the sides. And how do we measure distance? Distance is always measured perpendicular. That's the importance of these right angles here. We know we are measuring a perpendicular distance. So we have equal length of segment PX, PY, and PZ. So now let's take a look here. First, let's write this. This one goes from the angles and it goes to where? To the sides. So in case you haven't noticed, there's a lot of lines and you're going to have to look and see what's what. Because let's see if we can get both of these theorems here. I'm going to erase for a minute. Take a look at these two diagrams. Do you see a lot of the same lines? I see a lot of the same lines. We've got on this top one here, we've got lines going from a point that are perpendicular to a side and a line going from the point to the angle. And on the second one here, we've got a line going from a point perpendicular to a side and a point to an angle. What you're going to have to make sure of when you look at your diagrams, you have to look at them carefully. You are either looking for perpendicular bisectors or angle bisectors. So when you're looking at this point, what makes this point? This point is made by perpendicular bisectors. So we know that we are getting information about the segments that go to the angles. But on this one, here's our point of concurrency. What makes this point? Well, these are not perpendicular bisectors. They may be perpendicular, but they don't bisect the sides. We do have angle bisectors, though. So this point is created by angle bisectors, so we are interested in the segments that go to the sides. So this is why I have labeled these. This one goes from the sides, so we are interested in the lines that go to the angles. This second one here, the lines come from the angles, and so we are interested in the lines that go to the sides. So they look very similar, so you're going to have to look for those little differences that show you either perpendicular bisector of the sides or angle bisector. Okay, let's talk some more about our concurrency of the angle bisectors. Just like in the concurrency of our perpendicular bisectors, the point of concurrency of your angle bisectors is called the incenter of the triangle. And where do you suppose we are going to find the incenter? Inside. In any triangle, the incenter is always inside the triangle. This is different from what we just did. No matter what triangle you use, your incenter will always be somewhere inside. And our incenter here, remember, is equidistant to the sides. So we are going to use this to inscribe a circle. And we use our point P as the center. This is a radius, this is a radius, this is a radius. And so when we draw this circle, we draw the circle that is inside our triangle and intersects each side of our triangle. So that's kind of fun. Now, I'm sure that you're thinking, well, there must be algebra associated with this. So how do we use the incenter of a triangle? Well, we look here, and I see a point of concurrency. Now, I am going to figure out what type of point of concurrency this is. Well, we've got perpendicular lines, but they're not bisectors. But I do see angle bisectors, so this is angle bisectors, and angle bisectors go to the sides. So I am looking at these segments that go to the sides, and I know that these all have equal length. My point of concurrency is equidistant from the sides because this is using the concurrency of the angle bisectors theorem. So the distances from the incenter to the three sides are equal. So I know that this piece and this piece and this piece have equal length. Well, we happen to be told some things here. I know that segment GE here is 2x minus 7 long, and I know that segment GF here is x plus 4 long. Well, what can I say about them? I can say that they are equal because they are equidistant from our point of concurrency, from our incenter. So we simply substitute in and solve for x. And then once we find x, we can go ahead and substitute it back in. 11 plus 4, the length of this segment is 15 units. So how long are the other two? Well, we could substitute in. 2 times 11 is 22, minus 7 is 15. Or we could use the simple fact that they are all equal length and just say, well, we know this one's 15 because they're all 15 by the concurrency of the angle bisectors theorem. So these are easy. Seeing them is the hard part. So as always, geometry is a slow math. You're going to have to look and see what it is that's in the diagram. All right, that was 5.3. Circumcenters and incenters, concurrency of perpendicular bisectors and concurrency of angle bisectors.